made this page here. And I have all of these combined spectra here, and then for the chlorobenzene, I just refer to those and add a constant. So this is just referring to that previous, so you can't see the formula on this one because it's online, but I referred to the previous intensity of that chlorobenzene spectrum and then added a constant. That constant at the top is 1, this constant is 2. These are 0 for the stick spectra, and so these show up in the lower portion of that graph. The IR has a constant of 1 added to it, and it's normalized, so it goes from 0 to 1. And so it shows up in the second panel, and then the Raman has a constant of 2 added to it, shows up in the third panel. And so that's how you stack spectra. It's just add a constant to the spectrum and it stacks it up. Here's the benzene one. You see a much simpler spectrum because it's a symmetric molecule. And here, when you have an X that's up, the plus is missing, and when you have a plus, the X is missing. You see that these peaks don't line up. You know, like this peak doesn't have a corresponding peak there. And so you can see that this molecule is symmetric and has an inversion center. And then here's both spectra on the same plot without the sticks. So these are the 3 figures that you need for your report. And so here's the IR for both the benzene and the chlorobenzene, and here's the Raman for the benzene and chlorobenzene, just to show you know, the more complex chlorobenzene spectra in both types of spectroscopy. Now, as far as the assignment, I thought I would dig into that for a little bit, and it is not clear. Let's see. So I've been working my way through this. Here's basically all of the having trouble with the web version of Excel, but I've got all of the output from Gaussian right here, and then these are the spectral peaks, and you know, it's not clear which ones are lining up. The major ones are pretty clear, so that's why I scaled back the requirements. If you can match, you know, 5 of the major peaks here, and you pick the ones that are most clearly aligned, it doesn't have to be the top 5, but it has to be 5 of the major peaks, I'll be happy, because that's the same skill you would do for all of them. Okay, is try to figure out, okay, does this line up better with this peak or that peak? Use the intensities from Gaussian as well, because they can be a guide. And so instead of trying to do all 14 transitions, really 30 in Gaussian, 14 peaks that we see in the infrared, let's just practice. We'll get 5 of those peaks assigned, and so that'll be good. Any questions on that? Thanks. Right? Because it's a difficult assignment, and so that's probably why I haven't found it in the literature yet. So, great. The benzene, you should be able to assign all of them. Those are in the NIST table, and so you're set for that. Questions about the schedule for Blackboard? There is no lecture this coming Friday. I'll be on travel, and so I'm going to put something on the PChem YouTube page and on Blackboard. But basically, you're just going to be practicing electron configuration. So this week is quite a bit of review with some new information added in about the symmetry of the orbitals. But, you know, do the review. That's part of why I was disappointed in some of the answers on the test. When I talked about Vesper theory, the implication is if you're rough in Vesper theory that you would go back and learn it. And if you don't have your freshman book anymore, that's not a problem. Everything's on the internet. And in fact, there's free books from OpenStax. And if you've never seen OpenStax, go there. It's an open or free textbook consortium through Rice University. And they have a freshman chemistry book that's pretty good. And so when I teach freshman chemistry, I use a free book, a PDF book. And it's also online, it's searchable. So you can go to OpenStax for any of the freshman concepts that you need help on. It's a good book. So you probably needed to review vector theory if you were rough on that. Well, this week we're doing electron configurations. Guess what? That's in the freshman book as well. So go to OpenStax, practice with that book. We're going to take it a couple of notches higher. One of the things is really digging into the exceptions to the rule, and also trying to explain the ionization trends. We'll get into that today. So let's dive into the material. So we're going to be working with atomic wave functions and electron configurations today. So I want to talk to you about these hydrogenic wave functions. We're in a different coordinate system now. We were, for this whole course so far, in a linear coordinate system, just the x-axis. And then when we put molecules in the Cartesian system, we have x, y, and z. So we have the three Cartesian axes. But that's not the best coordinate system to use for a spherical object like an atom. And so you could convert x, y, and z into r, the distance from the nucleus, if you put the nucleus at the origin. And then theta would be kind of like longitude, and phi would be latitude. So just like we have on planet Earth, we don't talk about our x, y, z coordinates. We talk about our longitude and latitude. That's like theta and phi. And so the distance around the equator of the atom would be theta, and then the distance down from the pole would be phi. And then the distance from the nucleus, from the origin, is the radius, or r. If we use that coordinate system, then the wave functions are much easier to deal with. So here's our potential energy term. We're now dealing with charged particles, so we can't just say that the potential is zero. So we have the Coulomb Attraction. We've seen that before. This is the distance of the electron from the nucleus. Again, we have two charges, a positive charge and a negative charge. The negative charge gives us this negative sign here, and then z is the charge on the nucleus. Now these are the hydrogenic wave functions. So they work for any hydrogenic system, not just hydrogen, but also if you have lithium and you take 2 electrons away, so lithium 2+, it only has 1 electron left, and so that would be a hydrogenic system. So any atom that just has 1 electron, these wave functions work perfectly for. Even all the way down here to, say, barium 55+. Now good luck pulling that 54th electron off of barium, or that 55th, because as you pull the electrons off, it gets more and more difficult to ionize. But barium 55+ would be a hydrogenic system. And so Z up here for that would be the nuclear charge on barium, which would be 56. It's the number of protons in barium. We're going to learn a lot more, or review a lot more about the periodic table today, as well as we go along. So you have the Hamiltonian, which is the kinetic energy and the potential energy pieces. You have the second derivative portion. In the denominator, we have the reduced mass, which again, here's the reduced mass. And for our situation, essentially the mass of the proton or the nucleus is so much more massive than the mass of the electron that just the mass of the electron is close enough for us. So this is the Hamiltonian. So here's the Schrodinger equation. So we want to look then at these wave functions, and because we can separate the variables of distance from the nucleus from the theta and phi parts, then we can have 2 portions to our wave functions. So that's, I guess, the first concept that you need to think about, and you can write this down. You have 2 parts to the atomic energy wave function, or the atomic wave functions, and that is the radial portion, which just depends upon distance from the nucleus. And then you have the angular portion, which has the theta and phi in it, has the longitude and latitude, if you will. The angular part is going to show up later on in what we call the angular momentum terms, and it's going to give us our orbitals. If you take a p orbital, if you think about the p orbital, you know, it changes as you go around the atom in theta and phi, but it really doesn't change in terms of distance from the nucleus, and we'll see that in a second. So we have this r part, the wave function for the atom. This r portion is the radial part of the wave function, and this ylm, and it depends upon theta and phi, is going to be the angular part. This y the function is called the spherical harmonics. Now that name is descriptive. Okay, think about what that name means. It's spherical, okay, that's clear. Okay, and it's actually the harmonics of a spherical shell. So if you take a spherical shell and bang it with a hammer, it's going to vibrate. Just like any solid object, like this ring here, this isn't a shell, a spherical shell, but it's a ring, and it has certain wave functions associated with it, and it will resonate. And so if I hit this with a hammer, you hear it? You hear those vibrations? You can actually see that there's resonances in that ring. Same thing would happen with a spherical shell.
Cool.
Not 100%. Again, we're frugal. Right? And so the spherical shell, if you bang that spherical shell, it's going to resonate. And so they knew those functions for the resonances of a spherical object. They knew them actually before quantum mechanics. And so then when they thought about the cloud, the electron around a nucleus, they said, oh, the solutions for the resonances of this spherical object would be the same solutions for the resonances of this electron around a positive nucleus. And so they just applied those wave functions to this problem. And that's where we get the shapes of our orbitals. And so you're going to learn more about the shapes of the orbitals today than you ever knew before. And so then this R part, this radial distribution function, is just, again, another one-dimensional particle problem. So putting all this together, the energy really depends upon just the radial portion for the hydrogenic atoms. And so this is the Hamiltonian with the radial wave function in it. We've got the kinetic energy part, which is the second derivative of the radial portion, and then the potential energy part here too. And then this angular momentum term comes out from the spherical harmonics and ends up affecting the radial portion. So you can solve for the energies by doing this really extreme second derivative. Or if you do it the integral form, it's quite a complex integral. So these are the solutions, the energies for the hydrogenic system. Okay, so we have a new principal quantum number, N. And so that will be the shell that we're in. And then we have subshells that we'll learn about in a second. Even though L is present in the potential energy portion, it doesn't make it, or doesn't survive the differentiation, and doesn't end up in the energy equation. So for the hydrogenic or one electron wave functions, we don't have any difference in the p orbitals, the m sub L quantum numbers, and we'll go through the quantum numbers here in a second. What I really want to focus on here is the energy equation. This yellow region is just showing you the potential energy of an electron in close proximity to a positive nucleus. So this is the shape of that Coulomb Attraction. And so there's a well, right? The electron is down in a well close to the nucleus, but it doesn't collapse into the nucleus, and we'll see why. Essentially, the volume goes to zero as it gets close to the nucleus. But you see these wave functions, and way down here, we call this the 1s wave function. And so this is the ground state for the electron. This is n equals 2, n equals 3, n equals 4, n equals 5. So that seems strange. As n is going up, we see an increase in energy. Okay, but n is in the denominator. How is that the case? How are we getting a higher energy with a larger n? It's because the energies are negative. So look where 0 is in the hydrogenic system. 0 is up here. That's very different than where we set 0 for the particle in a box. You know, in the past systems, all of the other systems were putting the 0 energy down at the bottom, like around the ground state, or like in the vibrational wave function, a little bit below the ground state. But for the hydrogenic system, the reference point for energy is a completely separated electron and proton. And so then as we bring the electron and the proton together, then they start to drop in energy. So the energies are negative. So as mass goes up, see here, mass is in the numerator. As mass goes up, energy becomes more and more negative, so energy goes down. And that's the same kind of thinking that we had in the particle in a box. So our intuition is still the same. As the mass of the system goes up, the energies drop. As the quantum number goes up, again, these energies are negative, quantum numbers in the denominator. So as the quantum number goes up, the energies go up. Okay? It becomes less and less negative. And then nuclear charge. As nuclear charge goes up, the energies go down. And that makes sense as well, because we've got an electron attracted to the nuclear charge. If I make that a bigger charge, it's going to draw that electron closer and drop the energy.
This goes back to the previous slide, but L and ML were the radial quantum numbers?
We're going to get to what they are in a second.
Okay.
They're right here in the spherical harmonics. They're the quantum numbers within this spherical harmonics show. I just really wanted, but I want to emphasize this, that our thinking, even though a particle in a box, particle in a one-dimensional box is a one-dimensional system, very simple setup, zero potential energy. What did we learn from that? We learned that the mass of the quantum system is important. And if I have big masses, the energy levels crash down, and there's very little difference between them. If I have a higher quantum number, the energies go up because it's more excited. Right? There's no, in this particular case, we can't really tell that there's an L term in here. We can't really see that. But if we look at the plot of the potential energy, we do kind of see that as we go up in energy and quantum number, look how much farther apart the potential, how much more room we have, essentially. So the box is increasing dramatically as we go up. And what effect does that have on the spacing and the energy levels? Just like anharmonicity, when this potential curves so far to the right, you see that the spacing of the energy levels gets closer and closer together. So even though we don't have an L term, like a capital L, the length of the box in this hydrogenic system, we sort of do. You see it in the potential energy function. And as that potential energy gets smaller, you get essentially energy levels that collapse.
Are a lowercase l?
Well, in this case, there's no L, capital L, so you don't have that term in this one, but you see the effect. You see over here, this blue region right here, that's essentially the box that electron is in.
And then the nuclear charge, I mean, it's more protons that are in the nucleus, the more the energy goes down, is that what you're saying? Okay.
Yes. Yeah, because it's pulling on or attracting that electron closer to it. So this is the radial distribution function, or the radial wave function. Now, if you just have it without the volume element, without taking into account the effect of integration, where you're trying to integrate little volumes in this three-dimensional integral, then it looks like the wave function would drive the electron right into the nucleus. But you need to take into account the volume element for this wave function, because it decreases as r squared. And so when you take into account the volume element, the wave function goes back down to 0 at the nucleus. And so this is the wave function for a 1s orbital for that first electron on the nucleus. And you see that there's a most probable distance from the nucleus. It's 0 at the nucleus and it's 0 at infinity, but this is the wave function. Now, if we were to draw a line here where, let's say we square this, and we have the distribution function, the probability distribution, and then we integrate it, when we get to 95% of the probability of having the electron inside that mark, we could draw a line there, and then we could map that around the atom, and that would be the size of that orbital.
Is that what those?
And that's what those shapes are. It's like the 95% volume of the orbital.
Does the right side go to infinity? Like, does it ever hit 0?
Yeah, if you were to say, well, I want 100% of the electron, it would have to go up to infinity.
Okay.
And so when we make it 95, it really comes in. And so the 1s orbital's 95% electron density surface would be, say, this big, and then the 3s would be that big. so we'll look at these radial distribution functions next. So this is the 1s, and this is distance from the nucleus. So here we are out at 20 angstroms. And so for the 1s orbital, here's the most probable distance, the maximum of that wave function. Now that's not, I mean, it's not real sharp, right? I mean, it could be really close to the nucleus, it could be far away, it could be almost 5 angstroms away. You know, so that's quite a distance. For a hydrogen-hydrogen bond, it's about 0.9 angstroms, okay, between in an H2 molecule, but yet that electron cloud goes out quite a ways. Look at the effect that it has when you go to the 2s orbital. So this is the 1s orbital. This orange curve is the 2s orbital. Look, it goes up, down, and then up again, and then down. Why the 2 bumps?
Does that have to do with like constructive interference between the wave functions?
Not constructive interference, but do we see higher order wave functions have nodes in the particle in a box? Yeah, same thing in the radial distribution function. So you've got n equals 1 wave function, the next one goes up and down, and then the third one goes up, down, up. So just like the particle in a box, we have nodes in our wave functions. But unlike the particle in a box, we don't have a wall on this side. And so you see how the wave functions are kind of stretched out to infinity. There's no wall over there, but yet you still see this wave-like nature. You ever take a string and swing it? You'll see the nodes. Okay, you wave it really slowly, and it'll get kind of big in the middle, and the end won't move as much. And that would be the sort of the n equals 1 wave function for a string. But the end is not bound, and that's kind of what we have here. The nucleus kind of binds one end of the radial distribution function, but the other end isn't bound. But yet it does still go to 0 motion. And so you can shake a string. If you shake it fast enough, you'll get a node in the middle. I should go get my slinky. So then the 2s orbital has 1 node. What about the 3s orbital? Here it is, this blue one. Okay, it goes up there, and then there's a node. Why are they all going up? Well, it's because it's the wave function squared. So we're looking at the probability distribution functions. So it goes up and is pinned to 0, comes back up again, pinned to 0, and then it comes back up. We have this large hump up here. This is the highest part of the 3s orbital, so we would say that's the most probable position for that electron in a 3s orbital. Look how far away from the nucleus it is. We're down here at 13 angstroms for a 3s. So here's the 1s, 2s, 3s. So that valence electron in sodium can be as far as 13 angstroms away from the atom. So remember the ball at target, that hydrogen, if that was a hydrogen atom, this distance from that ball at target for that one electron went from like Madisonville to Spring, and from Navasota over to Cover Lake Livingston. So that's just the 1s. Then the 3s would be all the way down to Argentina. Yeah. So that's why it's so easy to ionize sodium. Because that last electron is so far away from the nucleus, you can pull it off, and the atom's energy doesn't really change. So this, the very first time you have an orbital, that radial distribution function does not have any nodes. So you see the very first available s orbital is the 1s, and so then the 2s has 1 node, the 3s has 2 nodes, the 4s has 3 nodes. But let's look at the p orbital. So here's now the radial distribution function for the 2p orbital. P is the first chance you have. The 2p is the first chance you have at p orbitals. So it has 0 nodes. The very lowest one that you have is the 2p. You don't have a 1p orbital. And so the very first time you have a p orbital, that has 0 nodes. And this is radial nodes. These are nodes as you go away from the nucleus. Everybody follow that part. Okay, these are talking about radial distribution functions only. But the 3p is the second p orbital, so it has one node. So here's this pink is the 3p. It goes up and down and then up again and down. And it's kind of strange. The 3s is sort of further out than the 3p. Now the 3d orbital is the very first chance you have at d orbitals. And so it has 0 nodes. So here's the 3d, most probable position, and it starts out, it stays 0 for quite a while, but then it comes up and then goes back down. So these are the radial distribution functions for an electron in an atom. Now let's start talking about the angular distributions. And to do that, we need to look at the other quantum numbers. So these are, let's sort of a 3D picture of the internal nodes. Okay, so this would be the 2s. You see this is a radial node. In all directions I have that wave function passing through 0. And don't get caught up when you're thinking about, well, how does the electron get from one side of that 0 to the other? This is the wave function that describes the electron. So you're looking at a single electron with this wave function. Now, if we had a tiny enough gun and we could hit that electron, we might knock it off at this spot here or that spot there, but if we aimed right there, we would never hit it. But I don't like talking about the electron being smaller than the whole wave function. Okay. This whole shape of this wave is describing a single electron. So a single electron is described by that whole wave that's waving. Now let's go through the quantum numbers. We've been talking about N. N is in the energy equation, and that's the principal or primary quantum number. We call it the principal quantum number, but that means the primary quantum number. It tells us what shell we're in. And that starts at 1. It does not start at 0. So it goes 1 all the way up to infinity. So it's unbound, and it's integers, just like all of our quantum numbers. Then we have the angular momentum quantum number. This is L, and this describes the shape of the orbital. Now, we've got all of these numbers, and so, again, this is review from freshmen. Since we have all of these quantum numbers, we've used letters to describe some of them. And so this is the one that has the letters associated with it. So the angular momentum quantum number is lowercase l, but we put letters with it. So L equals 0 is an S orbital, S orbital. L equals 1 is a p orbital, and so on. So this is review, yes? So S goes with L equals 0, P goes with L equals 1, D, 2, F, 3. But it keeps going up until you reach N minus 1. So this one has a bound on it. It always starts at 0, and it goes as high as it can go until it bumps up against N. So that's why we don't have a 1p orbital. Because if N equals 1, then N minus 1 is 0. So all we can have is an L equals 0. That's why we don't have a 3f orbital. Okay, because if N equals 3, then N minus 1 is 2. And we can't get to F. We can get to D, so we have 3d orbitals, but we don't have 3f orbitals. So you have to know this. This has to be like the back of your hand. This is straight up freshman chemistry. And it is explained by the periodic table. Notice the very first period, we have only 2 elements in that row, and that's your 1s. If we had 1p's, then we would have a whole lot more elements right there. But we don't have any 1p orbitals. So the periodic table is arranged based upon these hydrogenic wave functions. Next we have the m sub L, or the magnetic quantum number. And the reason it's called magnetic is there's no energy difference based on these quantum numbers unless you put it in a magnetic field. And so you can see the m sub L effect, the m sub L quantum number effect, if you put these atoms in a magnetic field. And if you have the electron interacting with the orbital, if the orbital has angular momentum, then you can see that any kind of spinning charge or charge with angular momentum is going to create a small magnetic field. And so you can have spin orbit coupling. So you can see some of this M sub L effect by the electron's own mini electric and magnetic field. So we have the magnetic quantum number, and it is bound. So this is minus L and plus L. So as L changes, the M sub L's change. So let's pick an L equals 1, so a P, set of P orbitals, and this is what gives you the subshells, the number of orbitals in that subshell. It goes from minus 1 to plus 1 with integers in between. And so for an L equals 1, you have a P orbital, and you can have M sub L minus 1, 0, and 1. And that gives you your PX, PY, and PZ. There's 3 P orbitals because of the M sub L quantum number. There's 5 D orbitals because it goes from minus 2 to plus 2 with 1 and 0 and minus 1 in the middle. And so that's why there's 5 D orbitals, and that's why there's 7 F orbitals. Okay. Because that goes from minus 3 to plus 3 with 0 in the middle. So it's 2L plus 1. That's the number of the orbitals. Pardon?
Repeat the last thing you just said.
It's 2L plus 1 is the number of orbitals that you have. So if you have F orbital, then it's 3, L is 3, and so you'd have 7. You'd have 7 individual orbitals in that subshell. So it'd be the F subshell with 7 individual orbitals. And the 7 orbitals would be described by that M sub L quantum number of minus 3, minus 2, minus 1, 0, 1, 2, 3. So there's your 7. And then lastly, the electron has its own intrinsic spin. And that spin can be plus or minus 1/2. Again, with all the numbers, we just call that up and down, and we use arrows. So when we draw an arrow up to indicate an electron, where it has a spin quantum number of plus 1/2, and we draw the arrow down, it has a minus 1/2. Now we can assume that spins are up and then do later on the Clebsch-Gordon series, which will take into account all the combinations of the spins. And so we don't always have to worry about whether it's spin up or spin down. We can calculate all the possibilities very simply. So these are the 4 quantum numbers, the address, if you will, of every electron in an atom. And what's interesting is that every electron has to have a unique address in an atom. So what does that mean? Well, that means you can only put 2 electrons in an orbital because there's only 2 types of electrons, spin up and spin down. And so once you try to put a 3rd electron in the orbital, it's going to have the same 4 quantum numbers. It's not allowed. Every electron has a unique set of quantum numbers. And that's how we get to our population of only 2 electrons per orbital, because the M sub L is a particular orbital. So the 2px has an n equals 2, an L equals 1, x would be one of the M sub L's, minus 1, 0, or 1. Okay, so that's a particular orbital, and then you can put a spin-up electron in there, and a spin-down electron in there, and then when you try to add a 3rd electron to that, it's going to match one of the other 2 electrons, and so it can't go in. It can't have the same set of quantum numbers. This is the designation for these. It's the principal quantum number, the angular momentum quantum number. For specific orbitals, you need to include M sub L, and then the number of electrons in this orbital. So, like you can talk about the 2s, M sub L is 0, 1 electron in that orbital. 4p02, so that's saying that orbital is completely filled. It's got 2 electrons. M sub L is 0, L is 1, and N is 4. So you should be able to take any one of these designations and pull out what is N, what is M sub L, what is, how many electrons are there, and so on. Don't worry about if it's 2p, x, y, and z, which one of those is M sub L, 0, 1, or minus 1, you can't tell. Okay. So you would have to define it somehow with a magnetic field or something, and say the magnetic field is in the z direction, and then you would figure out the relationships. So let's look now at the shapes of the orbitals. So we have the p orbitals, we have some d orbitals. Let's go through these individually. Okay, so let's look at the p orbitals. This is L equals 1. We put them in the Cartesian directions. It makes it easy, especially with the character table, because the character table has x, y, and z defined in it. And so we can look at these orbitals and put them in the character table. Now, if it's on an atom that's in an octahedral system, then we can know what the symmetries of these orbitals are in the octahedral character table. But what if it's carbon and it's in a tetrahedral system? Then we use the tetrahedral character table, and we can put those orbitals in that system. Now, what's being shown, I think this is the piece of information that you're missing from other classes. Remember the ring example. If I slam my ring down on the table, it's going to oscillate in a particular way. So I've got my ring, and I've slammed it down on this table really hard. It's going to compress this side of the ring. It's going to compress it. Right? It's going to shrink on this side. And it's going to bounce. And when it bounces, it's going to be oscillating like this. I'm missing the markers. So what I have drawn on the board is the oscillation of this ring. After I've slammed it on the desktop, it oscillates. And at some point in time, the ring is deformed. It's egg-shaped. And it's higher than it used to be on the top and smaller than it used to be on the bottom. It's deformed. But there's a place around the waist that's not changed at all. And then, sometime later, now it's bigger on the bottom and smaller at the top. So it's shrinking and expanding like that. But around the waist, it's not changing. And so if I were to take this and from the origin, plot the change in the ring as I go around in theta and in phi, as I go around the top, these would all be further out. Here it'd be 0, but here these would be further out. So on the top side I'd have a plus, and down here these would be closer together. And down here it would be minus. And then sometime later, these would be shorter, these would be longer, and so this would be plus and minus. So when we're talking about plus and minus in these orbitals, we're not talking about charge, we're talking about oscillation. And so if I were to plot this out, that's what that would look like. It's largest here, it's 0 there. It's shortest here and 0 there. So if I'm plotting this out, this is the largest point of deflection. This is 0 deflection. This is the largest point of contraction, and this is 0 contraction. Okay? So this is showing that this ring system is oscillating up and down. If we take it just from a ring and make it into a cloud, we have the same thing, and that's what we see in these p orbitals.
So like a camera to show them that the ring is actually doing that?
See this right here? Yes, you could do that. You could have a high-speed camera and see it deforming. And so this right here, these lobes are showing you how the electron cloud is oscillating. So it's oscillating in the y direction, or the x direction, or the z direction. And so at some time later, the electron cloud is deformed up, and sometime later it's deformed down, and that's moving in the z direction. And so that orbital has the same symmetry as z. We call it PZ, the pz orbital. And if you take all three of these together, the electron cloud is oscillating equally in all three directions. And that's what you see when you add all these orbitals together. You still see a spherical shape when you have a filled subshell. So this is just the first option for having a node, a radial node, an angular node. Let's look now at the d orbitals. So L equals 2. Remember that xy shape that we had? Here's the dxy. It goes positive, negative in the four quadrants of the x and y axes. This is the dxz. So in the xz plane, it goes positive, negative. It just has two nodes. And so it's kind of squishing here and expanding there, and sometime later it squishes here and expands there. And it has two nodes where it's not squishing or expanding at all. And so hopefully this is new information to you. I mean, we see these orbital shapes, but we never really think about, they're just describing the oscillation, the wave nature of the electron cloud. This one is down here is the dyz, so it's the yz plane, and again, plus, minus. It's that yz, or two axes times each other. Then those are in between the axes. We have orbitals that go along the axis as well. Here is the x squared minus y squared. So these are on the axis. The x squared means it's the same in negative x as it is in positive x. And it's opposite sign of the y portion, which is the same in positive y and negative y. So it's the x squared minus y squared. So the x's in this case would be positive and the y is negative, and sometime later they swap. But it's the same kind of shape as it is in these three examples, but it happens to be along the axes instead of in between the axes. Now notice the z direction wasn't used at all in this orbital. And so if we're going to combine it in with things along the axis, we need to use the z twice. We want to use every axis the same number of times. And so that's the simplest way to describe this one. This is the d2z squared minus y squared minus x squared. So this is z squared. It's twice as large as the deformation on the x and y axes. And it's x squared and y squared have the same sign. And so it's a circle. So what's the equation for a circle? X squared plus y squared, or minus x squared minus y squared, same thing. Okay. So I have twice the z-axis minus the x minus the y squared. And so that's where this donut comes in the middle. And so this is got a strange set of nodes that's two cones that come out, the top and the bottom. So those are the d orbitals. But they're kind of understandable. We've seen the symmetry of x times y. We've seen that in the character table. So if I have carbon in a tetrahedral character table for methane, what do you think the d orbitals are going to, what symmetry they're going to have? I just look up. If I've got the dyz orbital, I find it in the character table. And I see what the symmetry is. If it's in an octahedral system, like copper ion and water, and it's got 6 waters around it, and it's an octahedral system, I find the dyz orbital and put it in to the octahedral character table and find out what the particular symmetry is, and then I can do my selection rules and my transition dipole list. Here are the f orbitals. I'm not going to go through all of them. But here's f orbitals, and then we have g orbitals, h, I, j. It just keeps going. Now, what do you think it does as we get all the way up to something ridiculous like the j orbital? We got so many lobes and so many nodes, it starts to look like a sphere again. Yeah. We start to lose the quantum nature of its angular dependencies. So it starts at a sphere, it gets kind of crazy in between, and then it ends up being a sphere again. Okay, as you get bigger. As the box gets bigger, it starts to look just more like a macroscopic object, and you lose the quantum nature again. So it's in these middle regions where it's interesting. We have interesting nodes that you can point out to. But look at the f orbitals. It's very similar to the d orbitals, only with more nodes. So this idea of angular momentum, what's the deal? Well, it's the, you know, if you've got this motion in the molecule, or in the atom we're talking about, and you've got an electron in it, it's a like spin. It's, we call it intrinsic spin. And if you've ever, in physics, did y'all ever have the bicycle wheel where they spin it up and give it to you? And you sit you on a rolly seat and it starts to spin you around. You try to twist it, and it's hard to twist because of conservation of angular momentum. If you've ever used a gyroscope, where you spin it up and set it on there, it doesn't want to fall because, again, concentration of angular momentum or conservation of angular momentum. It's also why a bicycle is easier to balance when you're moving versus when you're standing still. So once you get some angular momentum moving, then it wants to be conserved. And that's one of the things that is the same in classical physics and in quantum mechanics, is the conservation of angular momentum. The interesting thing, though, in the quantum realm is that angular momentum is quantized. And so these spins in the atom can have certain values, not any values in between. So they are quantized, and we can't see those quantum effects unless we put things in an electric or magnetic field. And so the Stark effect would be putting it in an electric field, the Zeeman effect would be in the magnetic field, and we can do spectroscopies associated with those things. We can also see it emerge in spin-orbit coupling. So the electron spin coupling with the M sub L quantum number. And we will get into that with term symbols. So we're not into term symbols yet. We're going to do electron configurations first. So next we're going to practice on the electron configurations, and that will be your practice for Friday. I just wanted to see today how far we got. And so Friday will be a sort of an online or on your own exercise. Here's the deal. If you need to review, go to the OpenStax book. It's also in your textbook. Then we're going to focus on the exceptions. So you've got to learn the rules very well so that you recognize the exceptions. So I'll go through the data in a quick online video to get you primed up, and then have you work those problems in your problems notebook. And that'll count for your data. So see you electronically on Friday and